Okay, so I want to look at this problem. Question 11. Determine and solve a PDE that models a traffic light turning from red to green. So we're going to have to, the main thing here is to really just figure out what the initial data is, what the initial conditions are. Okay, so the PDE that we're dealing with, partial T rho plus minus 2 UM over rho M rho plus partial x rho is equal to 0. Here is the maximum velocity of the cars when the density is 0, and rho is the maximum density of the cars. So just to give us things that are kind of easy to work with, let's pick rho m. We'll say that the maximum car densities is just equal to 1, and we'll say that is equal to 2. Okay, so units, pick out whatever units you want so that this makes sense. Okay, again, the exact units aren't going to be so important. What will be important is the analysis that we do for this PDE. So the PDE then becomes partial T rho plus, okay, so is 2, so this is going to be minus 4 rho plus 2 times the x derivative of rho is equal to 0. And what are the initial conditions going to be? Well, let's think about it this way. Let's say the traffic light is located at x is equal to 0. And then if it's a red light, we'll say that to the left of 0, we're at maximum density, which would be rho m is equal to 1. And then after the traffic light, all the cars have moved on, and the density is going to be 0 here. So we have rho of x comma 0 is going to be equal to 1 if x is less than 0, and it's going to be 0 if x is greater than 0. All right, so what are the equations going to be? T dot is going to be the thing multiplying the t derivative of rho, so that's going to be 1, t of 0, 0. X dot is going to be the thing multiplying the x derivative. So it's minus rho plus 2, but this will be minus 4 rho plus 2, but on the characteristic, rho is equal to z. So this is minus 4z plus 2, and x of 0 is just equal to some generic x naught. And finally, z dot of s is going to be equal to 0 because, as always, this is z dot. Z dot of 0 is equal to 0. And now the initial condition is either going to be 1 if x naught is less than 0, or 0 if x naught is greater than 0. So let me go ahead and draw the axis. So this is the axis here, and let's solve for the equations. Well, the t equation we'll do first. This gives t of s is equal to s. Next, I can't do the x equation yet because it involves a z, but I can do the z equation. And z of s is just going to be equal to z of 0, which again is going to be 1 if x naught is less than 0, and it's going to be 0 if x naught is greater than 0. And then finally for x, well, this is going to give me x of s is equal to minus 4 z naught plus 2 s plus x naught. And then defining this piecewise, if x naught is less than 0, z naught is equal to 1, so it's going to be minus 4 plus 2, so that's minus 2s plus x naught. And if x naught is greater than 0, this just becomes 2s plus x naught. Okay, so now let's sketch some of these characteristics. And again, just to be able to color code things, I'm going to do this in, let's say, this horrible yellow color again. So this is 2s plus x naught for x naught greater than 0. Okay, so for these characteristics where x naught is less than 0, again, this is going to be for all values of x naught less than 0. That's the x-intercept. I'm actually going to draw it for x naught is equal to 0 as well. The slope is minus 2. well, sorry, if we look at this, we get something like x is equal to minus 2t plus x naught. So the slope is minus a half. So we're going to have something like this. So horrible line here. I'm trying to draw a dashed line. This is kind of the boundary characteristic where we're going to have the, these sort of weird things happen. So we'll have something like this. And then all of these characteristics, these purple characteristics are all parallel to each other. And I know that over here, rho is going to be equal to 1. For the yellow characteristics, going to be over here. And again, it's for x not greater than 0, but I'm going to do 1 through 0 and just do it as a dashed line. And all of these are all parallel. And I know that over here, rho is equal to 0. So I can start writing out my solution. Not u. Rho of xt. Rho of xt is going to be equal to 1. Okay, so this purple line right here, this purple dashed line right here is t is equal to minus x over 2. And this yellow line is t is equal to x over 2. Okay, so the density is going to be equal to 1 when t is less than minus x over 2. T is greater than minus x over 2. And we know it's going to be equal to 0 when t is less than x over 2. When t is less than x over 2. Okay, now what happens is we need to figure out what it's going to be when t is in between these two. Okay, if t is bigger, okay, and so it's going to be points that are in this part of the plane. Okay, so again, if this is my generic AB and I look at it, what I'm going to call a characteristic through those points. Okay, so what is the property of a characteristic? So what does a characteristic satisfy? Well, it's sort of instantaneous slope. It's derivative. It's a line, so it's just its ordinary slope. The slope m is equal to t dot over x dot. And in this problem, t dot is 1 and x dot is minus 4 rho plus 1, or plus 2. Okay, but for the characteristic that goes through the origin and the point AB, the slope is just b over a. So I've got minus 4 rho plus 2 is equal to a over b. This gives minus 4 rho is equal to a over b minus 2. If I divide both sides of this equation by minus 4, it's 4 is equal to minus a over 4b minus or plus 1/2. And if you want to get a common denominator here, you need to multiply the 1/2 by 2b over 2b. And so this becomes 2b minus a over 4b. And so over here, we would get 2t minus x over 4t. Notice I can write this inequality. I can multiply it by minus 1. And I put the minus sign here and change the sense of the inequality. So it'll be greater than, and then I can actually multiply it by 2. I'm just doing it this way to maybe make it a little easier for me to think about. and this is going to be 2. Okay, so then this region right here is going to be when we've got minus 2t is less than x, and x is less than 2t. Okay, so let's sketch a few solution curves so we can see what's going on here. So this is the x-axis, this is the row axis. When t is equal to 0, it's a fairly simple setup. We've got the density is going to be 1 over here, and it's going to be 0 over here. Okay, now let's look to see what happens when t is equal to 1. When t is equal to 1, this will be minus 2, this will be 2, and the solution is going to be equal to 1 when x is less than minus 2t, so it's going to be equal to 1 here. It's going to be equal to 1 here, and it's going to be equal to 0 here, and then it's just going to be the linear interpolation between the two going that way. Okay, and then in general, what's going to happen is for a different value of t, let's say this is just t is equal to a, this is going to be minus 2a, this is 2a, we're going to be equal to 1, maximum density here, 0 density here, and then just the linear interpolation between those two there. Okay, and think about what happens. I mean, we know what happens when you're at a red light and it turns green. What happens? Well, the cars start moving, and then as the cars start moving, what happens? Well, the densities, so the density kind of is getting thinner and thinner as we move out, and as you start moving, as the first car starts moving, this information that the cars are moving are kind of having to propagate backwards, and you still have some cars here that are still stopped before the information is able to propagate back to them. But then as everybody starts to move, the density of the cars spreads out, and farther down along the road it gets spread out more and more and more, and it's still 0 back over here where the information hasn't gotten to it yet, and then it just sort of spreads out, and this sort of whole density the whole density thing is sort of spreading out and moving down the road. Okay, just think about what happens when you're sitting at a red light and it goes from red to green. Okay, and this is what the profiles look like for different values of t. So again, it's important to remember here that the axis here is x and rho, and x and rho. Okay, so this is a traffic flow equation. In a moment, we're going to look to see what happens when a light goes from green to red. Something interesting happens in another way that's even more difficult to deal with. And before that, we'll get into this concept of shocks and things like that. Okay, that's it for this video.